In this video, we're going to introduce a scale for being able to measure very small concentrations of hydrogen ions. As we will see in biology especially, but also in chemistry, that the concentration of H plus in a system is extremely important. For example, human blood normally has a hydrogen ion concentration of about 4 times 10 to the negative 8 molar. Very, very small, right? 10 to the negative 8. That means there are 7 zeros here. So 0 0.1, 2, 3, 4, 5, 6, 7, 3, 9, 8 molar. That's very, very small, right? Incredibly small. And it turns out that if we, either add or subtract H plus from this number, we'll die. Or be very, very, very sick. Probably die, though, for any prolonged period of time. Our bodies are incredibly insensitive to changes in... they're incredibly sensitive to changes in H plus concentration. And so if we end up going to about 0.000000006, dead. Or 0.0000002, also dead. Either way. So we're not very good at adapting to changes in H plus concentration. But look at how horrible these numbers are. Nobody wants to count all these zeros. And we're going to see that many H plus dealings, as it were, use incredibly small numbers. So we're going to use something to kind of fix that, so we don't have to deal with all these numbers. We could talk about things in terms of nanomoles or micromoles, micromolar, but we'll see that unfortunately there's a variety of things that are happening here. In the stomach, H plus concentration is 0.1 molar. And in bones, it's 0.123456789. I'll just say 1 there, molar. So it's very hard to say, okay, we're going to focus on using nanomolar or micromolar here. It's tough because all of these are very varied, right, in their concentrations. And so we see that in lieu of using our metric prefixes, we're going to use a logarithmic scale to describe these. And first, though, I want to introduce how this logarithmic scale is going to come about and how we're going to use it. And it takes into account something that we've seen before. Two water molecules can interact together to form H plus and OH minus. Fine, we'll say H3O plus will be good. Both of which are aqueous. And as we see, this is water reacting with water. One of them is acid, one of them is base. Doesn't matter which one. We end up with H3O plus and OH minus, hydronium and hydroxide. This reaction happens not very often, or not very frequently, but it happens. And if we were to go ahead and illustrate the equilibrium constant of this, remember for equilibrium constants, we do not include pure liquids or solids. So for the equilibrium constant for this would simply be H3O plus times OH minus, because the waters they're liquids, so we're not going to include them. And it turns out that, much like any other constants, at least at 25 degrees Celsius, this one happens to be 1 times 10 to the negative 14. Again, we're going to omit the units. It would be molar squared, but we don't need the units here. Important to note that this is at 25 Celsius, and it's still a rounded number. It's not quite 1, but why make it harder on ourselves? Let's just say it's 1 times 10 to the negative 14. So that means that at normal, nothing else in the water, That means normally in pure water that H plus is equal to OH minus. Remember, H plus and hydronium are the same thing, which will both be, 1 times 10 to the negative 7. Remember, when we multiply things together, the exponents get added. So 10 to the negative 7 times 10 to the negative 7 is really 10 to the negative 14. So both of those are equal to 10 to the negative 7. And so we're going to see here that we've seen some of these values that are well above that and well below that. Like here with the blood, we had 10 to the negative 8. The stomach, we have 10 to the negative 1. The bones, we have 10 to the negative 10 or so. Hopefully I know how to count the zeros. So with this, we have a variety. And so we're going to kind of standardize this kind of pure water concentration of hydrogen. And what we do is we're going to use a logarithmic scale. We're going to use a logarithmic scale to compare H plus of different solutions. And so if we take the log of this number, so if we say log of H plus is log base 10, by the way, this is not natural log, just regular log. Well, then that means that this number would be negative 7. Right? 0, 0, 0. But because we see that most hydrogen concentrations are with negative exponents, meaning that they're very small, we actually will use a negative log. We're going to take the negative log of both sides instead. If we do that, logs destroy units, by the way. We get 7 here, positive 7, because we're doing the negative log of it. And what we're going to do is we're going to have a special name for this. We call this pH, where P means negative log. So P technically stands for power. Power of hydrogen is what pH stands for. And it means the exponent, right? So the exponent here, how logarithms work, remember they take an exponent and move it to be in front of the decimal, and everything else comes after it. You're probably noticing that I've put 3 zeros here. This 7.000 only has 3 sig figs. So remember our sig fig rules for logarithms, which we kind of glossed over, is that for logs, only numbers after the decimal are significant. So I'm just going to go ahead and point that out here. This number is only 3 sig figs. Notice because our original number was also 3 sig figs. So with logs, only numbers after the decimal are significant. So 7.000 only has 3 sig figs. The 7 is there to tell us the exponent. That's what happened with that 7 there. So that negative 7 becomes the 7. And remember, times 10 to the negative 7 does not impact sig figs, right? That's just a how big or how small is the number. These 3 sig figs here are what we end up with in our what's called the mantissa, the after the decimal part. So only numbers after the decimal will be significant for logarithms. So 7.000 is 3 sig figs. That aside, we can go ahead and take a look at the negative log of some of our other values. Say if we do the negative log of 3.98 times 10 to the negative 8th, which was our blood concentration of hydrogen, we get that the pH of this, which is the negative log of that number, will be 7.4. And since I have 3 sig figs here, I'm going to need 3 sig figs here as well. I might just be estimating this. I happen to know it's 7.4. There may be some actual decimals here. Here, fine, we'll be good. We'll use our calculators. So, negative, where is my log button? There it is. 3.98 EE negative 8. Doing this, aha, I didn't lie to you. There it is, 7.400. So, important stuff, by the way. Make sure you know how to use your calculator for logs. Again, I can kind of help. There's really only two options. You press your log button and then put in the number, or you put in your number and then press the log button. Your calculator will very clearly say like syntax error, if you do the wrong one. So play with your calculator, make sure you can do these. So with that, again, you can use your phone. Phones generally have logs, maybe. I don't know. Let's find out. Do phone calculators have logs? Maybe with the fancy like sideways one. Indeed, my phone has a log button right here. And so I would just put in log whatever. Although phones can be kind of tedious as calculators, in my opinion. I think I prefer a real one, but that's just me rambling. Anyways, with this idea, we can calculate the concentration of or once we know the concentration of H plus of a particular solution, we can turn it into a pH. And we'll see that our pHs will run from roughly 0 to 14, where 7 is right in the middle. 7 was our pure water, and we will describe this as neutral. Anything greater than 7 we will call basic. And because the concentration of OH minus and H plus is a constant, that's a fixed value, if your H plus happens to be a little bit less, that means your OH is more, right? Because the two have to multiply together to make our constant. And so, by the way, we often call this constant Kw the water ionization constant. We'll use that a lot, especially in the next video. But anything that's going to have a pH higher than 7 means your H plus is getting lower and lower. Remember that since this is a negative log, a bigger number means less acid. So a bigger pH equals less H plus. So the lower your pH is, the more acidic you are. The higher your pH is, the more basic you are. And we're going to see that anything between 0 and 7 we will call acidic, therefore. So lower pHs, lower than neutral, we call acidic. So anything less than 7. This blood, as we see 7.4, will show up right here. Blood is slightly basic. Our stomach acid down here at pH 1 by the way, it's got the word acid in it. That should help. But it's strongly acidic, right? It's HCl that's in our stomachs. And so roughly around 0.1 molar. It depends on a lot of biological factors, you know, how soon it is to your next meal and all that fun stuff. So stomach acid is there. We'll see that many kind of plant things, many plant-based products or cleaning materials tend to be more basic, and a lot of foods tend to be more acidic. So tomatoes, coffee, that sort of thing. When we're looking at plants, that's more the like tea. No, tea is slightly acidic. What I mean by that is, like, I don't want to say cocaine. That's what came into my head, but cocaine is basic. Cocaine is a base, and it's something from plants. So like a lot of like chemicals that we get from plants, those tend to be bases. So solutions of those will be basic. Solutions of like food, if you blend it up, tend to be more acidic. Milk, that sort of thing, they tend to be more acidic. So just for your own information. Generally speaking, bleach is probably the most basic thing you have in your house, unless you have lye for like Drano. Uh, Drano and lye use the same thing, sodium hydroxide, and that's going to be quite basic. So we're going to see that there's a whole variety. So in our next video, we're going to practice our calculating pH skills, and we're going to relate H plus to OH minus. And so there's going to be a lot of math. Grab your calculator for that one.